In this video, we're going to take a quick look at two concepts that have to do with the same types of compound events that we were talking about in the previous section. The first is called conditional probability. And the idea is that conditional probability let me write it down here. Conditional probability can modify the probability of one event given that we know some condition has occurred. So what I mean by this is a good example is it turns out that about 15% of men are above 6 feet tall. And so if you ask, what's the probability of a randomly selected man being greater than 6 feet tall, you would say, oh, that's about 0.15. But if I gave you an additional piece of information and said, now the person that we're interested in is a professional basketball player, well, that's going to change our estimation of the probability of them being over 6 feet tall. So if we ask what's the probability that a man is over 6 feet tall given that he plays professional basketball, it's going to modify the probability that we're looking at. So conditional probability, let me give you kind of a quick definition. Conditional probability states basically that, let's just write out a sentence here. The conditional probability of an event B, given that an event A has occurred, given that an event A occurs, is denoted with this symbol. We do the probability of B, and then a vertical line, and then the A. So this means B given A. The probability of B given that A occurs. And it has a formula that I'll write down as well. It's given by the following. The probability of B given A is equal to the probability, let's do that. The probability of A and B divided by the probability of event A. We use this formula when A and B are not independent events. So when one has an effect on the other. So we use this when events A and B are not independent. And the idea in this case is that independent events, the outcome of one doesn't have any impact on the other, but when they're not independent, the outcome of one will impact the other, as we saw in the example that I mentioned just a minute ago. So an example of this, let's think about this, maybe it has to do with, like a good example would be with maybe playing cards. So if I just ask you, what is the probability of drawing an ace from a normal deck of cards? And so in this case, the event that we're going to be, I'm going to call it B, event B, is drawing an ace. Don't know why I capitalized it in one place and not the other. Let's make them both lowercase. There we go. So when I ask, what is the probability of drawing an ace? Well, in a full deck of cards, there's 52 cards, and of those, 4 are aces. It's one of 13 suits, so you can write that as either 4 out of 52, which simplifies down to 1 in 13, if you write that out. But now if I give you the additional information that another event has already occurred. So what's the probability of drawing an ace from a deck of cards given that we've already drawn one ace from that deck of cards? So what is the probability of drawing an ace from a deck of cards given that we've already drawn an ace. We've already drawn one card and it was an ace. So in this case, we're saying the probability of B given some event A. So let me define A first before I write this down, actually. So event A is going to be that the first card drawn is an ace. And event B is the event that the second card drawn is an ace. Well, are these two events independent of one another? And the answer in this case is no, because drawing an ace on that first card changes the odds of drawing a second ace. So if we were to replace that card back into the deck and have 52 cards again with 4 aces, then they would be independent. So if I pulled a card and then shuffled it back into the deck, they'd be independent every time I pulled a card. But that's not the way we normally do it. So in this case, when we draw the first card, there are 4 aces out of 52 total cards. By the time we get to the second one, assuming we've drawn the first card and it's an ace, there's only 3 aces left, and instead of 52 cards, there's only 51 cards left. And so the probabilities will change. So in this case, the probability of B given A, we can figure out that it's going to be 3 out of 51, because there's only 3 aces left out of 51 total cards that are left in that deck. So it changes the probability. And in this case, you can actually simplify this down to 1 in 17 chance if you do some simplifications on that fraction. But coming back up to, let's see here, the formula at the top, I know that it's also supposed to be equal to, so if we weren't able to logic our way through this by just kind of thinking about the scenario, if we were forced to use this formula up here, let's see what that would look like. In this case, we'd have probability of A and B over the probability of A. Well, we already know the probability of A, that first card being an ace, was 4 out of 52. But this piece up here is harder. What is the probability of drawing an ace for both the first card and the second card? And so this is where this gets tricky. And we actually will often do this problem in reverse. We could figure out what's the probability of drawing an ace for both the first card and the second card by reversing this equation and multiplying both sides by the P of A. So we know that the answer is 3 out of 51. We know this answer over here is 4 out of 52. I could multiply both sides, and we're going to get a big ugly number up here. So that is another way that you can do these problems, is sort of in a reverse direction. So keep in mind, this is actually the hardest part of this problem, the probability, figuring out this probability of A and B. And so we'll talk about how we can figure out now what is the probability of A and B in other situations. Because basically right now, this is about as far as we can get on this problem. This is now the tricky part. How can we figure out this probability? Okay. So that's going to bring us to, let's just write down the second one, what I'm going to call the multiplication rule. And this multiplication rule is going to be used when our two events are independent. So this was when they were not independent, and oftentimes this is going to be really hard to figure out. In a lot of the problems you'll see in the homework, this will be given and this will be given, and you'll use them to plug into the formula and get this value. But sometimes they're not. And so we'll see how can we find this when we have independent events. So the multiplication rule basically tells us that if A and B are independent events, then it turns out the probability of A and B is going to be equal to the probability of A times the probability of B. We're going to multiply them together. So let's take a look at an example. In this case, I want to think about maybe like flipping a coin. In the case of flipping a coin, the events are independent. When I flip the coin and it lands on heads the first time, that has no bearing whatsoever, again, on whether or not the coin will land on heads a second time. It's not like you use up a heads by flipping a coin and having it land on heads. So if I let event A be that the first flip is heads, and event B be getting the second flip to also be heads, and I want to know what's the probability that the first flip is heads and the second flip is heads. Well, in this case, those are independent events, so I can just take their product. So what is the probability that the first flip is heads? It's a 1 in 2 chance. What's the probability that the second flip is heads? It's also a 1 in 2 chance. And when we multiply them together, we get a 1 in 4 chance of getting heads both times. And as we saw back when we did the sample space for this scenario, we saw that we could get heads, 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 tails, tails, heads, or tails, tails. And sure enough, what's the probability of getting heads on both the first and second flip? It is a 1 in 4 chance. So it matches the way that we did these problems previously. So you'll be able to use this again whenever the events are independent. And it's a quick and relatively straightforward thing to do. It'll work in some of those cases, but we really do need to check whether or not the two events are independent. If they're independent, we can use our multiplication rule. If they're not independent, we're stuck using, we're stuck using the conditional probability equation up here. And that one tends to be a little bit more complicated to try to, if we were to try to back out what the probability of A and B is. It helps if we already know these other values over here. So you can try some problems on the homework if you'd like. Again, this section is going to be extra credit, but I thought I'd at least give you a brief introduction into these concepts.